All right, we'll do that one more time, just in case you haven't got it all memorized yet, or haven't gone to YouTube and downloaded it yet. But yeah, the Element Song by Tom Lerner. Feel free to look it up and download it. I'm sure he won't mind. He's probably dead by now. Anyhow, it has all the element names in it. I'm sure you got all that memorized and everything, but that's good. All right. So, chapter 18. Due to ice and so forth, we will not be doing any demonstrations up at the school because I can't get there. Couldn't get there, although it is nice today. And so I guess as good a chapter as any because chapter 18 doesn't have a whole lot of demos anyhow. It's a little more all up in our heads. Okay. One thing though, before we do, there was a thought question which some people responded, some people very correctly, and said if you had that was posted in the announcements, and it said that if you had a proton and you joined it with an electron, what would tell me what the properties of that new particle would be. And basically, you have a positive and a negative, equally positive, equally negative, put them together, and well, yes, it is neutral. But not only is it neutral, it would weigh slightly bit more, not much, but a little bit, because it's got an electron and plus a proton, so it weighs slightly more. And guess what? Basically, that's the definition of a neutron. A neutral particle that weighs a little bit more than the proton. Okay, and so it's probably a little bit more complicated than that. There's some other energy that's released and blah 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 and things like that. But basically, a electron plus a proton gives you a neutron, or a neutron is a proton plus an electron. Now that will be more important when we get to chapter 16 with radioactivity and all that good stuff, and we will talk about that then. Okay, but just something to kind of keep in mind. Have we go on. One thing other also on the last quiz, NO3. Oops, some people haven't taken that yet. Hang on. Pass on that. Okay, we'll come back to that. But it's very important whether it is neutral, which is one on the quiz was, or if it has a charge. Okay, but we'll talk more about that later. Okay, so let's talk about atoms. Okay, we talked about a couple things. One, I'm gonna go back and touch on the idea of electronegativity, the idea of hanging on to electrons or letting them go. Electronegativity is a number, and we won't worry about the exact number for most of these, but how strongly do they hang on to their electrons? And as you get over toward the metal side, you'll notice that the numbers get small. The height of these little columns represent how big the number is. They get smaller and smaller, not only as you go this direction, but then as you go down farther here. Okay, now it makes sense. The smaller the atom is, the closer those outer valence electrons are to the protons, so they're harder to get away from. As you go down here and you get more and more rows, then those electrons out on the edge are way away from the protons. Yes, there's a lot of protons, but they're way down in the nucleus, and these guys are way out on the edge, so they're easier to take them apart. Okay, now the one exception to that, of course, you notice up here is hydrogen. Hydrogen has a fairly high electronegativity because it's just one proton and one electron. There's nothing between them, no buffering, no nothing, and so it does have a fairly high electronegativity. And because of that, sometimes hydrogen, in fact, you'll see on some charts, they will list it over here next to helium and say it's really more like a nonmetal. It can act like a metal and have a positive charge, which we'll talk about, or it can act kind of like a nonmetal sometimes. So it's kind of iffy. It doesn't know which way to go. Okay. All right. Now, we talked about the drawing electrons, and maybe I should have done that. I don't remember if my lecture on the video if I was more clear about this, but as you fill up, all except for the first row are going to have 8 electrons on the outside row. The first one has 2, and then after that, I have 8. And when they fill up, technically, there are what we call sublevels, and they spread themselves out through the sublevels. It's kind of like if you had a 4-bedroom house with or just a big bedroom with 4 bunk beds in it. Well, if you let the guys go in there, say you got 8 boys that are going to go in there. Well, the first 4 are going to grab their own bunk bed. Then they have to start pairing up, but they're going to want their own little area first. So what happens is on each electron on the outside layer, the valence electrons, which are the only ones we're really worried about, when they first fill up, say you have 4 of them like carbon does. One's going to jump in this little sublevel, one's going to get on this side on this little sublevel, one here and one here. And when you draw your atom, I usually do that. One here, one here, one here, one here, and then go back and pair them up. And that's what they would do. They would take their own sublevel first, then if there's time, and if you're more, you keep adding them. So like go to chlorine has 7. So then they would start pairing up with each other. And it doesn't really matter where you draw those pairs up. On sides, whatever. And They may not be technically at right angles and everything, but they're going to be spread out, those four subgroups, okay? And they're going to try to each get their own, and then when they have to, they'll start pairing up, okay? And these are those outside layers, the valence electrons. Now, a lot of times we will draw these. These are electron dot, Lewis electron dot structure, or Lewis dot structure, or whatever you want to call them. And since those inside electron layers, they don't change, okay? They can't leave, they can't gain, so we don't worry about them. We only draw the outside layer. And so that up to 8 dots, just like you have up to 8 electrons in that outside layer. And so because of that, um, that's why it looks like this. We're just drawing those because they're the only ones that really care to us. Now, in order for electrons to join together, they need to have these unpaired electrons. This guy's looking for a match. This one's looking for a match. This one's looking for a match. They're ready to gain with someone. If they're full, for example, on chlorine, this one's full, this one's full, this one's full. This is the only one that's really available. The unpaired electron, single, available, there we go, to react with other elements. So it can only react one place, and chlorine has a -1 charge. If we did sodium, sodium only has one electron out here, so it only has one unpaired electron, so it can only have a +1 charge, okay? And so that's kind of the deal here. And so when you have these out here, the electron dot, it shows the valence electrons and which ones are unpaired, because those are the ones that can have a charge or can share with each other, okay? They're the electrons that are available, okay, on the market, if you will. All right. So that's called the electron dot, and it's just the number of dots. So if you're in the first column, hydrogen would have 1 dot. That's it. Helium would have 2, but they're paired together because they only have that first layer that can hold 2. The layer's full, they're paired up, they're not interested. In fact, you'll notice this whole column over here, guess what? They're all paired up. That's one reason these are the inert gases. They can't react with anything because they don't have any unpaired electrons, okay? But if you go here, there could be 2, but once again, this level can hold 8, so that's unpaired. All right, and then 3, and then 4, and then 5. We're skipping the transition metals because they get a little complicated, but the other ones, 4, 5, so now they're starting to pair up. 6, 2 pairs up. 7, 3 paired up. 1, only 1 unpaired, and then finally the inert gases where they're all paired up, okay? And therefore, they're not interested. Now, if you're, we used to call this the happy atom rule. If an atom wants to be happy and have a charge, because no one wants to be all by themselves, right? They want a charge thing and join up with things, right? So if you were, say, lithium, you could either fill up 7 electrons to have a full outside layer. That's what makes atoms happy. They want to have that outside layer full. Or you could get rid of 1, and then your other layer that has 2 electrons, that first layer, would be full, and you would be happy, okay? Which is easier? Well, the lazy atom rule says it's going to do whichever one's easier. It's easier to get rid of 1 than it is to gain 7. So lithium would get rid of 1. If you get rid of a negative, that gives the atom a +1 charge. If you have 2, you get rid of 2, it gives it a +2 charge. Guess what? Get rid of 3, a +3 charge. All right. But then you get to carbon. Carbon could either gain 4 and fill it up, or it could get rid of 4 and get rid of it. And it can do either one. And it can be a plus or -4, depending which it does, which is one reason why carbon isn't everything, because it's very versatile. It can be positive, it can be negative, it can share, it can do a lot of different stuff, and it has a lot of options. It has 4 different pairs that can react with other pairs. And so that's, shouldn't say pairs, unpaired electrons from other atoms, okay? Then once we get to nitrogen, or 5, now they start pairing up, and you have less options, okay? But if you have 5, it's going to be easier to fill it up because you only have to gain 3 instead of get rid of 5. But since you're gaining 3 negative electrons, it's going to be a -3 charge. 2 in this case is going to be a -2. You can gain 1 here, so a -1 charge. And finally, the ones over here that are all tied up, and they don't want to gain or lose any of them. Okay, they just want to hang on to them. So in general, metals over here are going to be losing electrons, and therefore they have a positive charge or a cation, and the nonmetals are going to gain and therefore become more negative. And we know these are more electronegative. They want to hang on to their electrons. These are more willing to give them away. Okay, so that ties back to what we talked about that. All right, now we're going to talk about atoms of the same substance. Okay, how do they hang on to each other? All right, I'm going to start with metallic bonds first. Okay, that seems a little out of order maybe according to the notes, but we're going to do that first. Okay, in a metal, you have your uh, nucleus and all the inner layers. Okay, and that's what this M up here represents. That's the nucleus and those inside electrons. The outside electrons that are circling out here that we show in the electron dot, they don't hang on to them very good. Remember, metals don't hang on to electrons very good. So they're just wandering around here in between them. Okay, so you have positive uh, positive charged nucleus and center, and then you got all these negative electrons, and they just kind of share the electrons. They just kind of bounce around from one atom to the next, but that holds them all together. The positive is here, and then all these negative electrons that kind of bind them all together. So that's called a metallic bond. We call this the lattice, just means a framework of these atoms with the electrons just flowing around here. Now, because that when an atom heats up, well, these electrons start moving faster and faster, and so it conducts the heat. They bounce into other electrons, and it passes that energy on to other electrons, and so that's why they conduct heat so well. Electricity is the flow of electrons. So if there's more electrons on one side and less over here, then they're going to flow from high to low, and they're just going to flow through the metal because the metals don't hang on to their valence electrons very well. And so this would explain why they are such good conductors of heat in metal, because they have such freely flowing electrons in them. And in a metal, that is how it is set up. Okay, now we can mix two metals together, and then we have what we call an alloy, bronze, brass. We'll probably do an example showing how to make some, I believe, brass pennies next week. But we can mix the atoms together and make an alloy of a metal. But still, it's going to work very much the same. Instead of just one kind of nucleus and inner layers, you might have several interspersed, but still, they're going to share. Their electrons go flying around from one to the other, and it's going to hold them together as a metal. All right. Now, when we talk about, usually we talk about charges, we talk about if someone gains or loses an electron. All right. Okay. And these are what we call ionic bonds. An ion, remember cations and anions. Cations have positive ions. That's the metals usually. The non-metals gain electrons, so they become negative or anions. Okay. Ion just means it has a charge. Cation means it's positive. Anion means it's negative. Well, if we have metals, which tend to lose electrons, and they join up with a nonmetal, which tends to gain, well, what happens is, say for this example, potassium iodide, which would be salt substitute, sodium chloride would be the same kind of thing, or over here they have sodium fluoride, which is in our toothpaste. When you have a metal and a nonmetal, usually the metal doesn't want to hang on to the electron, the other one does, so it just gives it this electron. Well, that gives us a +1 charge. That gives the iodine, who has an extra iodine, electron a negative charge, and since they're positive and negative, they're going to stick together. All right, and the next one, if you had another Ki molecule, the I would be attracted to the potassium, and the K would be attracted to the negative here. And so they generally make a crystal shape of some sort. That's why salts tend to have crystals. Okay, it's going to have a crystal shape because these positive and negatives are going to stick to each other. Like if you had a bunch of magnets, they're going to stick to each other because you've got a north and a south pole. Well, positive and negative acts the same way with electricity. Okay, they're going to stick to each other because they have opposite charges, and it's going to hold them together. These are ionic bonds. Okay, and so a lot of the minerals that we will study about when we get to chapter 25 about geology are going to be ionic bonds, and they make certain structures depending on how their positive and negatives attract each other. They may make square shapes like salt. Salt is very square. Okay, if you have a big chunk of salt and you break it off, it's going to break into little square pieces. Okay, others may make hexagons or various shapes, but they're going to make different shaped crystals. Okay, a lot of our minerals that are found naturally are formed like this. Okay. Anything else? That's about it. Okay. Yeah, that's ionic. What if you stick two nonmetals together? Okay. What if they say, hey, I like the electrons, and the other nonmetal says, I like the electrons? Well, what are we going to do? Well, a lot of times they will share. It says, you want it, I want it, so let's share. Okay. Unlike people who tend to say, I want it, tough. Okay. But what they may do is say, hey, fluorine, for example, up here has 9. This one has 9. All right, but this one, if it shares it, sometimes it comes over here and this one's happy and full because it's all there. And sometimes this one from over here comes over here and this one is happy and full. So they kind of have a joint custody, if you will. Okay, they have joint custody of the electrons. And so that kind of holds them together because they're trying to share it. So they can both feel like they have 8 electrons in their outside layer, which makes them happy. Okay, hydrogen, same thing. They both have 1 in their outside layer. They want to fill it up to 2. So they just share and get together and they share it together. And so they feel like they both have 2, which they do about half the time. Okay, so they're called covalent because the valence electron is shared or with both of them. Okay, so that makes it a covalent. Okay, so generally this is with nonmetals and hydrogen, which we said can kind of be one or not. Okay, now if you have 2 fluorine atoms or 2 hydrogen atoms like we have down here, they're going to share it pretty equally because they have the same number of protons, they have the same number of electron levels, so they're the same distance from the positive neutron, so they can equally pull it both ways. Okay, but what if one of them has a stronger pull than the other one? Well, it's kind of like if you have a big kid and a little kid in the sandbox sharing the toys. Well, they may share them, but the uh, big kid may get the toys most of the time. Well, the same thing can happen when we have um, covalent sharing of electrons. Okay, you have an oxygen atom, for example, up here in water. It has 2 non-paired electrons that it could share. Both the hydrogens would like to share one. So what they do is they bond and they share this one and they share this one. But oxygen's a lot bigger. It has a lot more protons. Okay, and so it's going to have a bigger pull on those electrons. And guess what? Most of the time, these 2 electrons from the hydrogens are going to be going around the oxygen, which makes it more negative. The little hydrogen atom, which is one little proton trying to pull their electron back, are not going to have it most of the time, so they tend to be positive charge. Okay, and so they are what we call um, polar covalent. In other words, even though they're sharing it equally, it's not equal, and so you still have one side that's a negative pole and one side that's a positive pole. Okay, on the other hand, with oxygen right here, they're sharing, but they're pulling on it equally, and so that is what we call non-polar. It's like they're sharing equally, share and share alike, like true love, and they share it equally, and so neither one of them has a positive or negative charge most of the time. It's right there in the middle. Okay, now it can have to do with the shape. Part of the shape of oxygen is it has a bend in it where it bends like this, and so you end up with one side that's positive, one side that's negative. With carbon and oxygen, like carbon dioxide with 2 oxygens on it, okay, they could be uh, polar, but the problem is they're pulling this way and they're pulling this way. It's an equal pull in both directions, so both ends are going to be about equally positive or negative, and you don't get this that you do in water. Okay, just kind of the way it goes. But anyhow, even though you have 2 different elements, they're both being pulled the same amount on both ends, so both ends would have the same charge if they did have a charge, and so it really is not a polar covalent. All right, it's going to be a non-polar covalent, even though you have different elements involved. Okay, but anyhow, so covalent means they're sharing it. Polar means that sometimes one side shares more than the other or gets the electron more than the other, so you have a positive and negative pole. Okay, they're not as strong as an ion where you have just completely different. The electron just goes and it's always over here and it's never over here, and so you have a positive negative and they stick together because of that positive negative. But it's kind of halfway between polar and ion and covalent. So polar covalent is kind of somewhere in between. Okay, now even with ionic compounds, we talked about like, oh, well, the sodium just gives up its electron to the chlorine, and so chlorine's always negative, and the sodium's always positive, and they stick together. Even there may be some sharing sometime. Okay, it's what we call a continuum. At one end, you have the ions, where they pretty much don't share. They just give it away one to the other, and the positive and negative attract. Okay, on the other end, we have the like 2 oxygen molecules where they're just sharing and sharing 100% equally, and there's no charge, positive or negative, either way. Okay, and as you go toward the middle, then you got a mixture of that. Okay, polar covalent can be anywhere in that middle. All right, and so they're if they're polar covalent, we say, well, they're a little like an ion, okay. But if they're more toward they're polar covalent, but they're more toward the covalence, non-polar covalent side, then mostly they share equally, but one of them still has it more than the other, okay. So just for the record, it's not just ionic, just covalent or polar covalent. There's kind of that polar covalent is the in between stuff, and some can be a lot more polar covalent, and some can be a lot less polar covalent. Okay, so it just kind of depends where they are on that. And technically, you can subtract their electronegativities. That's why we have that number. And by looking at the number, we can show you where it would fall on this continuum. Okay, the bigger the number, the more it is ionic. The less difference, the more alike they are. Therefore, they're going to share it more equally. They're going to be toward the nonpolar covalent side, but they're going to be somewhere in between there. And even the most ionic compounds may share sometimes. Okay, just once in a while. All right. Now, that's talking about how the molecules hold together, like a molecule of water or a piece of metal or whatever of all one element or something like that. Okay. Now, what about those molecules? In water, you have all these different water molecules. Well, how do they hold to each other? Okay. Or in salt, you have all these sodium chlorine. How do they control to each? How do they attract to each other? So now we're talking about attraction between molecules. All right, instead of just between atoms. All right, and now we're going to start thinking about molecules. If it was ionic, has an ionic bond, or even if it's polar covalent, it would have positive and negative poles on it. And we think of it as a marble that has a magnet in it. And if we were actually in person, or at least if I was up at school, I'd get out my magnetic marbles and show that they are going to stick to each other pretty good. Ionic ones, obviously, you got positive, each one's positive, negative, so you can just hooking them all to each other, and they're going to have very strong attractions between the molecules, and that's why we said they make crystals and very elaborate shapes, and they usually have very high melting points. Salt, you can melt salt, but you got to get it really, really high. Dissolving it in water, that's not the same thing. We'll talk about that next week. But melting salt, which you actually have liquid salt, it can be done, but it is very, very high boiling point. So ionic, they are strongly attracted. They have strong intermolecular forces holding them together, so they have high, very boiling points. Now, if you have polar molecules, they still have positive and negatives. They're not as strong as the ionic bonds, but they're still going to be strongly attracted to each other. So once again, they're going to have fairly high boiling points. Water, for example, has to get up to 100 degrees Celsius or 212 degrees Fahrenheit in order for it to break loose and become a vapor. But it is a liquid, not a solid, at room temperature. So they will hold together to each other very good. They have fairly strong attachments. All right, and they tend to be either solids or liquids at room temperature. Non-polar, they don't have any positive or negative. It's like if I mix glass marbles in with my magnetic marbles. They might get trapped between some of them, but if you kept moving them, eventually all the glass ones would fall out. Why? Because they don't have any attraction to those other ones, so they don't want to attach to them. They don't want to mix with them, and they just want to come out of solution. And so non-polar ones are very weakly attracted to each other, and so they have very low melting and boiling points. And many of them, like the oxygen atoms, the fluorine atoms we talked about that are joined to each other, where they're almost perfectly covalent, they're going to be gases because they don't really have much attraction to each other. They're just going to bounce around in the air because to hold them together as a liquid or a solid, it's just pretty tough, okay? Because there's hardly any attraction to them, okay? Now we'll talk more about dissolving things next week, but just real quickly, if ionic compounds like salt are mixed in a polar substance like water, they both have positives and negatives, so they will join up with each other, just like those magnetic marbles. If I get two different colors of magnetic marbles, but they both have positive and negatives, they're going to mix together pretty good, okay? And so they will dissolve in each other. So we say, and when it comes to polar or nonpolar, we say polar dissolves in polar. Okay, but you can't take a non-polar thing and try to dissolve it. Why? Because just like those glass marbles, they're not attracted to it, they won't mix with it, and they will eventually come out very easily. So it's hard to dissolve something like oxygen in water. Water holds oxygen, that's what keeps fish and other things that live in the water alive, but it's fairly small amounts. And so if it gets too hot or something and it's hard for it to hang on to that oxygen, you can have big fish die-offs and stuff like that. On the other hand, it's very easy to take ionic compounds like salt or other liquids that are polar covalent and mix them with water, because they both have positive and negatives, and they mix together and hang around with each other, and that's no problem. Okay, so we say like dissolves like. Polar dissolves polar. Nonpolar mixes fine with nonpolar, but they don't always mix very good with each other. So oil and water, oils tend to have nonpolar things, and so they don't mix very good. Oil and water don't mix. All right, now, so to summarize, let's look at some of the different combinations we could have. We've kind of talked about most of these, and you can kind of figure it out from what we said, but let's see here real quick what I want to be on this channel. This is just an example of different compound. Now, they probably should be kind of flip-flopped. If you have carbon with carbon, it's almost perfectly nonpolar. If you have carbon and nitrogen, there's a little bit more of an electronegativity difference, and so they could kind of be slightly positive or slightly negative. The little sigma thing here means slightly. The nitrogen side would be slightly negative, and this would be slightly positive, but not very much. Carbon and oxygen, like carbon monoxide, there's a bigger difference between their electronegativity, so they become more polar. And the oxygen side definitely be negative, the carbon would be slightly negative. Carbon and fluorine would be even a bigger number, so it would be definitely closer to the ionic side. Okay, just to kind of give an example of that. All right. Now, attractions. Which ones are going to be attracted to others? Okay, well, if you have an ionic compound, obviously, and say you put them with a polar substance, well, polar has a positive and negative side. If I find my pointer, okay, positive and negative side, and so this has a positive and negative ions, basically, so it's going to mix in there. So polar and ionic mix well. Now, sometimes we call it polar covalent because that's a big word. It's easier to say a dipole. In other words, they have two poles, positive and negative. So if you see the word dipole or you see polar covalent, it's the same thing. And I may say one sometimes and some the other. Okay? They have positive and negative. They mix well. They dissolve well. They can recrystallize. If you dissolve the water out, then the ionic compounds will go right back together and make their crystals. So they mix quite well. If you have a dipole and a dipole, or a polar covalent with another polar covalent, well, they have positive and negative sides, so they mix well. They will grab together. They're not going to be as strong as ionic. Okay. For example, in our DNA, we have hydrogen bonds in the middle. You know, it's a ladder with little bases coming out in the middle. Everybody remembers that, right? And they fit in the middle. But when you make new DNA, they split down the middle. Well, that's because they have these hydrogen bonds, which are basically a polar covalent to a polar covalent, okay? And so there's a little bit of a pull there. They'll go back together, but they'll also be easy to pull apart, which is very important when you're trying to make more DNA. So dipole to bipole, or polar covalent to polar covalent, they still have positives and negatives, so they will bind together, but they're easier to break apart because they're not as strong as these ionic bonds over here. Okay, and now once again, it depends on how polar covalent are they. Some are almost ionic, some are over here where they're almost covalent. Obviously, the closer they are to ionic side, then they're going to make stronger bonds, harder to split them apart. The closer they are to the non-polar covalent side, then they're going to be easier to tear apart and put back together. All right, which can be good or bad, depending on if it's something that needs to stay together or not. Now, there is something else, though, that can take place, and this is called an induced dipole, or an induced polar covalent. Okay, I'm not sure if I have something here. Let me check real quick. Here we go. Say I have oxygen. You have two oxygen molecules. If it's by itself, they will share equally. They don't really have a charge or not. But say I bring something like a water molecule. Okay, and a water molecule, this side over the oxygen is negative, this side over the hydrogen is positive. Well, if I bring this negative close to this one, it's going to repel the electrons away from this. So instead of sharing them equally, most of the electrons will run over here to the other oxygen far away. That makes this side temporarily positive and this side temporarily negative. Okay, so we have induced a dipole. Normally, two oxygen atoms would not oxygen atoms would not have a positive and negative side, but we have forced them to have one temporarily. And so, as long as that happens, it will be attracted to the water and it will dissolve in the water. This is why oxygen can be dissolved in water, because temporarily it is. But say this water molecule gets jostled away. Guess what? This is going to go right back to this. So it's a very temporary charge and temporarily allows it to dissolve. And this is why oxygen does not dissolve in water very well. In fact, if the water gets hot, these are moving around real fast, the water molecule is liable to bounce away. It goes back to this, and the oxygen might escape before another water molecule induces a dipole and causes it to be attracted to it. Okay, so that's very important. If you have an induced dipole, that's this bond right here, because the negative side here has repelled the electrons over here and made this side slightly more positive. It's a very temporary, weak bond. Okay, and so, but it does allow things that are normally non-polar covalent, don't have any positive, it allows them to actually dissolve in water and other polar substances, at least temporarily. Okay, but it's a very tenuous thing. It's not a permanent change. As soon as this oxygen molecule gets away from the bad influence or the influence of water, it will go right back to where it shares and shares alike. All right, hopefully that's as clear as mud. But a lot of this really will start making more sense, I think, as we talk about some of these other things. Hopefully next week we'll be back to normal. We'll have some demos and we'll have some demonstrations. We'll definitely see if we can make some gold and silver pennies, if nothing else. All right. Have a great week. Don't forget, still need to turn in your questions on Saturday night and then the quiz next week. And we still have one more week before the test. Okay, there'll just be a quiz this week, but next week there will be a quiz and a test. Something to look forward to. All right, hope you're not nearly as icy as you were. Hopefully a lot warmer, and things are going well, and internet and electricity is all going well. If there's any problems about that kind of stuff, let me know, and I can, if the internet goes out or something like that, let me know, and we will make adjustments for that. Have a great week.